Alright, hello class. In this particular video we're going to be looking at double integrals over polar coordinates, and this is probably the most famous transformation that there is, right? The UV transformations. The tricky thing about those is each new problem has its very own transformation that you usually have to come up with. However, for a lot of cases, we can use polar coordinate transformations, which is going to be the same transformation each time with the same Jacobian and all that. So really we have to do that work once and then just apply it as we need it. Okay, so where do we use polar coordinates? Okay, so to reiterate, polar coordinates give us the most important and or popular transformation that you'll use in double integrals, and specifically we use these when R is circular or closely related to a circle. So what do I mean? Well, let's think about this example here. Let's think about the example of the double integral over R of e to the x squared plus y squared dA, where R is the unit circle. Okay, so the unit circle, as we talked about last time, has a pretty nasty formula in Cartesian coordinates, right? It's x squared plus y squared is equal to 1. So if you wanted to set this integral up in xy coordinates, it'd be something like -1 to 1, and then the negative square root of 1 minus x squared to the positive square root of 1 minus x squared of e to the x squared plus y squared, right? dy dx. All right, what's not so nice about this is, well, one, the limits are disgusting, and two, the integrand is actually impossible to deal with, right? No matter what order we choose, this is going to be an impossible integral. So, well, what do? Well, we transform this into polar coordinates. Okay, well, what does that mean? Well, here's how it works. For every point in xy, right, let's say here's our point xy, and this could be any point. All right, this is determined by an horizontal value and a vertical value, right? This is basically telling us that we go out x and we go up y. These are often called rectangular coordinates because we're talking about them in terms of the rectangle that's made by x and y. Okay? However, each point also corresponds to an angle made with the positive x-axis. Okay? So every point we can completely determine it with a theta, an angle it makes with the positive x-axis, and the distance, which we'll call r, from the origin. So if we draw this line between the origin and the point xy, well, that's going to make an angle theta, right, between it and the positive x-axis, and it's going to have a length from the origin. Okay, and this is where we get our polar coordinates transformation from. So xy is what we call Cartesian coordinates, and what we're going to do is move that into our theta, which are what's called polar coordinates. Okay, and we actually already have all the information we need to make this transformation. We've seen this before. If we think of this instead as a vector, we know that this point can be written as r cosine theta, r sine theta. Okay, so that's what this point equals. We also know that this length r, using the Pythagorean theorem, gives us that r squared is equal to x squared plus y squared. Okay, so the transformation to go from xy to r theta is given as x is r cosine theta, y is r sine theta, right? And that's nothing new. We've been doing this since the very first lesson of this class. And r squared is x squared plus y squared. And there's one more we could do if we want that can sometimes come in handy. That's tangent theta is equal to y over x. All right, that may come into play every so often, but this is the main transformation here. Okay, this is the transformation. Okay, and so let's look at the Jacobian of this transformation. Okay, so the Jacobian of the transformation, which in this case we'll call j of r theta, instead of using u and v, we're just using r and theta here. It will be the partial derivative of x and y with respect to r and theta. Okay, so in other words, it will be the determinant of the matrix x sub r, x sub theta, y sub r, y sub theta. Okay, well, x sub r, well, if we take the derivative of x, which is r cosine theta, with respect to r, well, that makes cosine theta a constant, and the derivative of r is going to be 1, so we're just going to get cosine theta. Now, the derivative of x with respect to theta, well, now theta is our variable, so we're going to get negative r sine theta. All right, when we differentiate y in terms of r, so y sub r, that will be sine theta. And the derivative of y with respect to theta is going to be r cosine theta. All right, so we're going to do our main diagonal and our off diagonal. So we'll get r cosine squared theta, when we multiply these together, then minus a negative, so plus r sine squared theta. Okay, well, cosine squared plus sine squared is 1, so if we factor out the r, we're going to get r times cosine squared plus sine squared, which is 1, so the Jacobian comes out to just be r. Okay, so, and we don't need to introduce the absolute value because r is always positive. All right, so when we transform a double integral into an integral over polar coordinates, what we're going to end up with is the following. Okay, what we end up with is that double integral becomes this nastier looking integral here, where theta goes from, say, an alpha to a beta, r goes from some inner radius to some outer radius, f of r cosine theta, r sine theta, r dr d theta, right? The r is the Jacobian. Okay, it just comes out to be r. Now, this is typically how we always want this integral to go. We always want to do r dr d theta. That's typically the easier way to do it because usually it's our thetas that are going from constant to constant always. And what we're actually going to want to do is to try and always get all of these to be constant to constant. Okay, now if we go back to this example that we started looking at, which would have given us, this sort of mess here. what this would end up being is if I wanted the full unit circle, we could actually transform this into from xy into r theta in the following way. I want theta, well, I want to get the whole unit circle, so I want to go from, say, theta equals 0 all the way around to theta equals 2 pi. Right? That's the full rotation, so I want all of it. Okay? Now, this is where it can get a little confusing, because for r, when we talk about inner radius and outer radius, well, for each angle, r, that's the distance here, and it is going between 0 and 1. Okay, so you can almost think of it as an axis, but it's spinning around. Okay, so r is going to go from 0 to 1. All right, now e to the x squared plus y squared, well, e to the x squared plus y squared, well, remember the x squared plus y squared is just going to end up being r squared. Right, so we're going to get e to the r squared, then dy dx, that becomes r dr d theta. And now we have an integral that we can actually evaluate. All right, so integrating with respect to r, well, now here we couldn't set this integral up at all, right? This was impossible, but now that we have the r sitting outside, e to the r squared, we can do a quick u substitution now. Okay, so we're going to get the integral from 0 to 2 pi. I'll leave the r on this side. Integral of e to the stuff is itself divided by the derivative of the stuff, so divided by 2r, times r, right? And we'll evaluate this from r equals 0 to r equals 1. And this works because the r's cancel. Okay, so we're going to get the integral from 0 to 2 pi of e to the r squared from 0 to 1 d theta. So we're going to get the integral from 0 to 2 pi of e to the 1 minus e to the 0, which is 1 d theta. Okay, now this is just a constant, right? And whenever we integrate a constant, it's just going to be that constant times the difference of the limits. All right, so this ends up being 2 pi times e minus 1, and there we go. Right, we've turned an integral from something that we, well, can't evaluate to something we can, and something that actually ends up being not that tricky. Okay, so this actually opens up the possibility for lots of complicated circle-based things. Well, what do I mean by circle-based things? Well, that's what we're going to talk about when we mean polar rectangles. So polar rectangles are regions in polar coordinates where theta and r go from a constant to a constant. Okay, so when I say that r goes between 0 and 5 and theta goes between 0 and 2 pi, it might not be that confusing to know that, well, what that means is we could do it on the x-axis. R always goes between 0 and 5. So 0, and then let's say this is 5. All right, here's our r. And then we spin this around a full 2 pi radians, okay, to get the circle. Okay, so this gives us a circle of radius 5 centered at the origin. Okay? However, we can adjust this to say, let's see what happens if instead of letting r go between 0 and 5, we let it go between 2 and 5. But we still have theta going between 0 and 2 pi. Okay, well, theta going between 0 and 2 pi, it means we have a full rotation. However, r, instead of going from 0 to 5, it's now going from, say, 2 to 5. Okay, and that is what's making the full rotation. So this is what our region will look like. So what we've made here is sort of a disk shape, right? So with polar coordinates, it actually becomes very, maybe not very, but much easier to look at regions over, say, a disk than it would in Cartesian coordinates. Okay, interesting. How about I take this same thing and I adjust theta now. Let's say r is still going between 2 and 5, but now theta only ranges between, let's say, pi over 4 to pi. All right, well, the r is ranging the same, right? It's going from 2 to 5. But it's not doing a full rotation, right? It's starting at pi over 4. So here's the starting point, and it's from there that it ranges to the ending point, which is pi. So I should probably use different colors there for the angles. Right, so here's theta equals pi over 4, and here's theta equals pi. And r, going from 2 to 5, will be basically this portion of a donut here. Okay, so when I said before inner radius, outer radius, this is what I'm talking about, that when I go from the origin and map outwards, the first thing I'm going to hit is the inner radius, and the second thing I'm going to hit is the outer radius. So instead of left to right or bottom to top, it doesn't make sense to talk about polar rectangles that way. Instead, it's more starting angle, ending angle, inner radius, outer radius. Okay, and I just realized I put an r there instead of a theta. Sorry about that. For this next example, let's look at r basically staying the same, but now we're going to let theta go between negative pi over 2 and pi over 2. All right, so r goes from 2 to 5. And then negative pi over 2 to pi over 2, well, that's essentially doing this, right? So our starting theta is here, and our ending theta is here. So you're always going, well, what we're typically always doing when we're looking at polar coordinates is we want the angles to always go counterclockwise, okay, in the positive orientation if we can help it. So if we want this half of a disk, well, then we choose the smallest interval we can. And note, we can't do, it's common to say pi over 2 to 3 pi over 2, but that would be telling us this. Right? This side would be pi over 2 to 3 pi over 2, because you're always going counterclockwise if you can help it. All right, looking at another example, let's evaluate the double integral over r of 2xy dA, where r is given in the graph. So here we have this fourth of a disk, okay, shown here. All right, and we're going to want to do this using polar coordinates. And I tend to always want to do that if I ever see anything that is like circle-based or disk-based. All right, so that's always a good indication that you want to use polar coordinates, because if we don't, notice that if we do, say, bottom to top, here the bottom is this portion of a circle, while the top is this portion of the circle, and here the bottom changes. Same thing happens if we do left to right. Left to right, the first portion, the left, is this portion of the circle, but then it becomes this line. Okay, so either way we try to do it in Cartesian coordinates, we're going to end up with two integrals. But when and the limits are going to be nasty, because here this would be the square root of 4 minus x squared, and this would be the square root of 1 minus x squared. Okay. All right, so we want to move this to polar coordinates, and we do it by first establishing what our limits are going to be. Okay, well, in this case, it shouldn't be too bad, because all we need to do is find a starting theta and an ending theta. All right, so it looks like theta is going from 0 to pi over 2. Perfect. Now we need some limits on r. And here's where we do our outer radius versus inner radius. So if we go from the origin and span outwards, first thing we hit here is 1. And then the second thing we hit is 2. All right, so the inner radius is 1 and the outer radius is 2. And if you're taking the whole circle, you just go from 0 out to the radius. Okay, so this double integral becomes, well, the limits are going to be theta goes from 0 to 2 pi, or sorry, pi over 2. Okay, and r goes from 1 to 2. And now we just change this x and y into r's and thetas using our transformation, right? X is our cosine theta, and y is our sine theta. Then dA, remember, dA, which is dx dy in polar coordinates, comes out to be r dr d theta, because remember, r is the Jacobian. So we get r dr d theta. All right, so you get the integral from 0 to pi over 2, the integral from 1 to 2 of 2r cubed cosine theta times sine theta dr d theta. All right, now one thing we might want to do here is simplify these things, because 2 times cosine and sine, that's going to become, using this identity, we've used this one before, but sine of 2 theta comes out to be 2 sine theta cosine theta. So whenever we see that in an integral, it's actually going to be in our best interest to replace it with this. It just keeps us from having to do like a u substitution or something crazy like that. So what we're going to have is r cubed times sine of 2 theta. Then dr d theta. Okay, then from here, we'll do 0 to pi over 2, and now we'll integrate with respect to r to get 1/4 r to the 4th times sine of 2 theta, and we'll be plugging in the r equals 1 and the r equals 2. Okay, so we'll get 0 to pi over 2 times 1/4, or of 1/4, then it will be 2 to the 4th, okay, minus 1/4 times 1 to the 4th, all times sine of 2 theta. I forgot to put my d theta out here. Okay, so this will be a 16 over 4 minus 1 over 4. So I'll just say that's 15/4 times sine of 2 theta d theta. And now we've got it down to, well, a Cal 1 problem, right? So the integral of sine is negative cosine. Since we have a 2 in there, we need to divide by it. So let me put the 15/4 out here, and this will be negative 1/2 cosine of 2 theta. And we are going to evaluate this from 0 to pi over 2. Okay, so I'm going to leave this 15/4 out here. We'll have negative 1/2 cosine of, when we put in the pi over 2, we just get pi. Okay, then minus a negative, so we'll have plus 1/2 times cosine of 0. Okay, well, cosine of pi is negative 1, so we'll have negative a half, so we'll have a half plus a half, which will be 1, so it just comes out to be 15/4. All right, so this example is actually going to stretch all of our polar coordinates muscles here and all of our double integral muscles too, because it's going to involve visualizing the original curve in Cartesian coordinates, then converting it to polar, then transforming the whole integral into polar, then integrating, and et cetera, et cetera. So the first thing we need to do, if we want to evaluate this integral, which is the integral from 0 to square root 2, the integral from x to square root of 4 minus x squared of cosine of x squared plus y squared. So the first thing that leads me to believe that we want to use polar coordinates is, one, I see this x squared plus y squared, and I know in polar coordinates that that's just r squared. And I don't see the derivative of this sitting out here at all. Like if I saw an x or a y, I would know I could do a u substitution. But without it, the only way I can get that u substitution is changing this to an r squared, and then in polar coordinates this becomes an r dr d theta, which means that I can actually set up that u substitution that I need to make this work. But to get that, we're going to have to change the limit. So we've already changed what's going on in here, right? The integral is going to be cosine of r squared, r dr d theta. Okay, so what we really need to focus on is this, right? The limits. So how do we get the limits from this? Okay, so we need to take a step back to what we already know about double integrals, and that is if our y integral is the first one, then these are y equals x and y equals the square root of 4 minus x squared, and this is oriented from bottom to top. Okay, so we're going to graph these and see what we get. Okay, so we'll start with y equals x. Well, y equals x is the easy one. That's just this line here. Okay. And then next, the y equals the square root of 4 minus x squared, well, that is a little tougher, but that's actually a circle, because if you take y equals the square root of 4 minus x squared and square both sides and move the x squared over, you get x squared plus y squared is equal to 4. So that's the circle of radius 2, right, centered at the origin. And specifically, since it's the positive one, it's the top semicircle, right, not the bottom semicircle. Okay? So we have these two guys. And now we need to look at what's going on in the x's. So x is going from 0 to square root 2. Well, okay, so x, this is the x-axis. X goes from 0 to wherever square root 2 is. Okay, so if this is the bottom and this is the top, that means what we're really looking at is this region here. And we just need to know where the x value stops. Well, to figure that out, there are a couple ways. One is to just recognize that y equals x is going to correspond with a 45-degree angle, and so does square root 2 over 2. But if you don't just automatically see that, just set these two guys equal to each other and solve. Right? So if you take 4 minus x squared square rooted equals x and square both sides, right, you'll get 4 minus x squared is equal to x squared. So 4 is equal to 2x squared. So x squared is equal to 2. So x is equal to plus or minus the square root of 2. So that means that this is the x value square root 2. Okay, so we're looking at this region here. Okay, now, if we want to convert this to polar coordinates, we need two things, right? We need to know what theta is doing, and we need to know what r is doing. Well, r, I think, isn't too bad because no matter where I start, here or here or here, this is the circle of radius 2. So r is going between 0 and 2. It's the angles that may give us some trouble. And once again, if you just know what angle this is associated with, awesome. Okay, this one is pretty clear. That's going to be theta is equal to pi over 2. Okay, we need to know what this angle is. So some of you will just look at this and know what it is, but let's say you don't. Okay, how do you find this angle? Well, a couple ways. But I'm going to suggest looking at this, y equals x. Well, if y is equal to x, because that's sort of the line we're talking about right here, right? Y equals x. If y is equal to x, if we use our transformation, that means r sine theta is equal to r cosine theta. Okay, and if we divide through by that r cosine theta, okay, the r's cancel, and we'll get sine theta over cosine theta is equal to 1. And sine over cosine is tangent, so tangent theta is equal to 1. Well, when tangent theta is equal to 1, well, we have two possibilities. Theta is either pi over 4 or 5 pi over 4. Okay, so it's either here or here. Well, it's definitely this one. So this is a 45-degree angle, which we could establish from the fact that we have a square root 2 here. So if you, or you just know that it's a 45-degree angle when we have y is equal to x. Okay, a lot of ways you can get this, but even if you don't remember those things, you can still get that value from here. And notice here, this tan theta is equal to 1. yeah, that's neither here nor there. I don't want to muddy the waters anymore. Anyway, so theta is going from, pi over 4 to pi over 2. So we should have everything now to set up our new integral. Okay, so this original integral that we started with is going to become this new integral in polar coordinates, which is the integral from pi over 4 to pi over 2. Okay, then the integral from 0 to 2 of cosine of r squared r dr d theta. Okay, and now this integral we can actually calculate because we can do a quick u substitution, which is just one of my all-time favorite things to do. All right, so the integral of cosine of stuff is going to be sine of that stuff divided by the derivative of that stuff, which will be 2r. Then we'll have r. We're going to evaluate this from 0 to 2. Well, the r's will cancel, and again, that's how you know that your quick u substitution worked. If the original stuff doesn't cancel away, you haven't done it right. Now, you can leave a constant, but the variable stuff should disappear. Okay? So, applying our fundamental theorem of calculus step, we'll now have the integral from pi over 4 to pi over 2 of sine of 4 over 2 minus sine of 0, which will be 0, d theta. And we're basically done because sine of 4 over 2, that's a constant. So when you integrate a constant, you're just going to have that constant, right? The sine of 4 over 2 times the difference of the limits. So pi halves over, or pi halves minus pi fourths is pi halves. So we get sine of 4 over 2 times pi fourths. I think I might have said that wrong. So we're going to get sine of 4 times pi over 8. And there we go. All right, and that's all I really have to talk about when it comes to polar coordinates. So that should get you started on the homework. And as always, if you have any questions, feel free to let me know, and I will catch you all on the next one.